So in this video, we'll be discussing question 1, which is to do with industrial viscometer design. So this is just the question, and it is to design an industrial viscometer of your choosing, capable of measuring viscosity of semi-viscous fluids such as maple syrup or glycerin, considering variables such as viscometer dimensions, viscometer sensitivity, viscometer accuracy, and to just justify your choice of viscometer. So just to run through a couple of definitions before we start, just for viscosity, so viscosity is the resistance of a fluid to flow or to change shape. And in this case, we have semi-viscous fluids. As you can see, we have water-like, which have very low resistance, so they're really free-flowing. Semi-viscous have some resistance to flow, but they're not viscous. So viscous fluids have really high resistance to flow and they just don't flow easily. So we're kind of dealing with the middle scale here. So this is important for when we are looking for the type of viscometer that we're going to be using. So there are many types of viscometer that are commonly used in industry, and particularly capillary tube viscometers, coaxial viscometers, so they're your rotational viscometers, where the falling sphered viscometers are used most commonly in industry. There's also contact-free viscometers, so they're optical tweezers, and they just have a lot more sensitivity and accuracy. There's elasto viscometers, and there's many more types available out there. But for this, we are going to be looking at capillary tube viscometers. So the reasoning behind using the capillary tube viscometers is that they're suitable for laminar flow, they're suitable for semi-viscous fluids, which are the fluids that we're going to be examining. They provide isothermal flow, and there's another few reasons there as well. So the Ostwald capillary viscometer is the viscometer normally used, but I have chosen to go with the Oblond viscometer. It's quite similar to the Ostwald capillary viscometer, but it is more accurate and it's better for reproducibility for results. So this viscometer is placed in a thermostating bath for maintenance of temperature. You can see the two viscometers beside each other there. I'm also choosing to use automated equipment for higher accuracy. This delivers an accuracy of 0.001 per second, which is really accurate and really sensitive. This is why I chose the automated equipment for this case. So just with regard to the dimensions of the viscometer, we're really looking for the height and the radius of the viscometer. Now, it can be any height, but preferably it would be under 100 to 150 millimeters, and this is just for time efficiency because you don't want the fluid to be flowing for too long. But because the fluid is semi-viscous, the radius must be small enough to obtain an accurate reading. So this is approximately 2.75 millimeters for glycerol and maple syrup. So the viscometer measures volumetric flow rate, which can be seen in this equation below, and the viscosity can then be calculated by rearranging that equation, as you can see there. So each viscometer has its own constant, and if the viscometer constant K is known, the equation can then further be simplified to this, and the K represents the pi, or to the power of 4 over 8L, and it is calculated for viscometers with known radius and height, and this can just simplify calculations. Thank you for listening to this video, and I hope you learned something new.